Welcome to this explainer. Today, we're doing a deep dive into the real numbers behind coal washery units, and we're bringing a highly analytical, data-driven approach to the table. Look, if you're operating in the coal beneficiation sector, you already know the stakes are incredibly high right now. Traditional coal processing plants are seriously struggling to figure out how they're going to meet those looming 2026 carbon intensity targets. So our goal today is to uncover the hidden financial and energy leakages that are silently but very aggressively eroding your bottom line margins in the current fiscal year. We're going to bridge that crucial gap between what the financial auditors see on paper and the ground-level engineering realities to show you exactly where the capital is bleeding and, more importantly, how to recover it.
To get us there, here is a quick look at our roadmap. We'll start with the washery efficiency crisis, move on to analyzing operational bottlenecks, unpack the energy intensity of heavy media, diagnose pump and density leakages, and finally lay out a clear roadmap to optimized recovery.
All right, let's jump right into Section 1, the washery efficiency crisis, and specifically what this looks like on the balance sheet.
To put things into perspective, according to a recent commercial compliance audit by the Controller and Auditor General of India, Bharat Coking Coal Limited missed out on a massive opportunity to realize an additional 371.33 crore rupees in revenue. And it's super important to understand that this wasn't because of a drop in market demand. No, this was entirely due to severe operational misalignments and internal inefficiencies. These inefficiencies actually manifested as non-compliance under new environmental oversight, which ultimately caused them to miss out on higher realizable prices for wash, coking, and power coal.
When we take an impartial look at the audit data timeline, the project delays are pretty glaring. For example, at the Patherdih-I washery, mine production kicked off in June 2013, but the washery itself wasn't commissioned until August 2018. That is a staggering 5-year gap. On top of that, at the Patherdih-I washery, the contractor completely failed to finish the critical track hopper system, meaning the work had to be fully offloaded by February 2022. We have to remember, these aren't just arbitrary dates on a calendar, they represent crores of stranded capital and severely delayed throughput.
Now you might be wondering, what actually happens to the raw material during those years of delay? Well, the washability characteristics of the coal fundamentally change. By the time the plants were finally commissioned, the raw coal sitting there had become completely unsuitable for the original plant design. This created a massive gap between the plant's theoretical design capacity and its actual daily throughput performance. Operators were essentially forced into these really costly, inefficient blending procedures using raw coal transported all the way from the Damagonia mine just to make their feed usable.
Which brings us nicely to Section 2, analyzing washery operational bottlenecks and what it really means when we talk about sweating our assets. Current industry projections show that we're going to need an additional 20 million metric tons per annum just to feed new power stations. Faced with that kind of immense pressure and those strict 2026 carbon intensity targets closing in, operators are pushing their plants way beyond their design limits. This leads us to a really critical question from industry experts. Are we actually maximizing our process performance right now? And do we truly grasp the impact of inefficiency when we're sweating our assets above their design levels? Because the reality is, pushing an inefficient system harder doesn't fix it, it just amplifies your fiscal leakages.
Let's dig a bit deeper into the machinery in Section 3, the energy intensity of heavy media and the dense medium cyclone, or DMC, circuit.
If we look at the intricate routing of raw coal and dense medium through a standard pump-fed cyclone circuit, we see that raw coal and dense medium are blended before hitting the cyclone, where centrifugal forces separate the high-ash rejects from the clean coal. But let's zoom out for a second and talk about the kilowatt-hour consumption here. When you compare it to the rising power demands of froth flotation units used for finer particles, it is this specific, continuous loop in the heavy media circuit that is notoriously energy-intensive. This is exactly where your largest utility spikes are coming from.
So where exactly is that power going? Let's break that down in Section 4, diagnosing pump and density leakages, which we can essentially call the main power drain.
Some fascinating academic research out of a South African coal washing plant points to a shockingly common technical bottleneck known as the overpumping effect. Imagine having massive 200 kilowatt corrected medium pumps running for 16 hours every single day. Because of suboptimal pump speeds and aged, inefficient configurations, out of all the dense medium being pumped, only 25% actually makes it into the mixing box. A staggering 75% literally just flows straight back down into the tank. That is a massive, totally unnecessary draw of kilowatt hours, and it's costing operations crores of rupees annually for absolutely zero productive output.
Okay, We know the problem, now let's fix it. Section 5 is our roadmap to optimized recovery, where we engineer a financial solution.
According to advanced optimal control studies from the University of Pretoria, you actually don't need to completely overhaul your entire infrastructure to solve this. The secret lies in implementing real-time monitoring tools that let you adjust circuit parameters based on live power consumption data. By making just a minute adjustment to the medium density control parameter, specifically tweaking a mathematical parameter known as beta, from a baseline of 0 to just 0.1, you can fundamentally optimize how that heavy medium is being utilized in the system.
This isn't just theory either. This highly targeted step-by-step technical upgrade instantly yields a 3.54% reduction in total energy consumption for the dense medium cyclone process. Think about what that means. You are maintaining high resource recovery rates while strictly adhering to those upcoming 2026 water and energy usage mandates. You're getting better cleaning efficiency, less toxic gas emission during the burning of the final product, and you are drastically cutting down your power drain.
Let's translate that into hard numbers for the balance sheet. If you apply this 3.54% optimization to a standard plant running 15 DMC modules for 16 hours a day, the impact is huge. We're talking a daily saving of 7.91 megawatt hours. Over a year, that's 2.89 gigawatt hours saved. Financially, that equates to an annual cost saving of roughly $0.43 million US. It completely proves that using audit data to make minor engineering tweaks can literally secure crores in bottom-line margin preservation.
Industry analysts at Ernst & Young hit the nail on the head recently when they identified productivity improvement as the absolute top risk facing the coal industry today. Bridging the gap between your theoretical plant capacity and your actual daily throughput by reducing energy usage, it's no longer just a nice-to-have option. Given the new 2026 regulatory and environmental landscape, it is a critical mandate if you want to survive and stay profitable.
So, the audit data is totally clear, the technical bottlenecks are exposed, and the engineering solutions are right there waiting to be implemented. I want to leave you with one final, provocative question to think about for your own operations. Are you truly maximizing your process performance to stop the financial leakages in your plant? Thank you so much for joining me today for this deep dive. If you found this data-driven explainer valuable, please do like, share, and subscribe to the channel for more like videos. Catch you in the next one.